Okay, remember, this integral here, if we had computed that integral perfectly, instead of having these big wide rectangles, you'd have very narrow rectangles. Something like this. There'd be a rectangle here that would go all the way to the curve. It needs to be a little wider. Something like this, kind of a rough approximation. So imagine that as being much narrower. Then there'd be another rectangle. And on and on and on. And all of those rectangles would combine to fill the area that I'm now drawing. Something like that. Then it would fill all of this space completely. Oops, low, kind of like that. Question? Excellent. So next one. So go to number 4. So do page 4. Go. if this helps me kind of think of it. They want an equation for the position at time 35, so they want to know where is the plane right here. So the way I think of it is, at time equal 20, the plane is located at location 152. If I integrate the rate of change of the plane, or the velocity, for the next 15 minutes, so from 20 to 35, the integral will be this distance in green. That amount will be the change in the position of the airplane. Therefore, I need to take the 152 plus the integral to get the new position. That's where this formula comes from. Wave if you want me to say that again. So the plane is located here at location 152. During the next 15 minutes, the plane's position is going to change. This integral will calculate how much that change of position will be. So whatever that turns out to be, I need to add the green amount to where the plane was to find out now where the plane is at time 35. Please.
Is it better for us to think of it like that, or I just rearrange the equation?
Either way. Either way. 2 points for Ashlyn. Either way. I do think it's helpful if you can practically think of what's happening, but I also find the algebra to be extremely helpful as well. So both ways are good. Anybody else? And then this one, the way I think of it is, the plane's way over here at time equal 40, where the location is 234. So here's time equal, what's that? Hold on. So here's where time's equal to 40. The integral is going to calculate how much the change in position was from time 0, which is over here somewhere. And that's why you're subtracting the integral, because you got to go back in time to find this one. Like Ashlyn said, this one to me I can kind of talk out pretty easily with a story. This one's a little harder to make a story fit. The algebra is just an easier way to do that. Okay, one warning for the upcoming test. So it's not like tomorrow or anything, but the next test is all written, okay? And you got to be very cautious. Don't put a subtract when you mean plus or vice versa. You will lose quite a few points for doing that. So just, I keep telling people, don't rush on an AP test. Just be deliberate. Take your time, okay? Don't go slow, but don't rush. Please.
So usually you're like adding if you're trying to find a position that's like beyond what they give you, and then subtracting before previous.
It's a good way to say it. I'm taking a current position. I'm trying to find a later position, like later in time. So I've got to add the change in the position to where I am, and then the opposite to find the earlier position. It's a good way to think of things. Points for Noah. Anybody else? Please.
So when it gives you S of 40 equals 234 miles, can you just plug that in when you write your equation, or is it just better to?
You can just plug it in.
Okay.
Yeah, you don't need to write S of 40. Just plugging in is fine. So, 2 for Isaac. Any questions here? So, keep going on 4 then. What's the answer to C? Please raise your hand. Let's write it down right. Please raise your hand if you correctly found 164. Just check in the room. 2 points. Wave if you need me to talk about it. So I'm doing the integral from 5 to 35. I'm supposed to use 3 subintervals. Good to there? So midpoint sum means look at the first subinterval and pick the value of the velocity that is in the middle of each subinterval. So that's my V. I multiply by dt, which means the width of the subinterval. So that's why I've got 9.5 multiplied by the width, which is 10, followed by 4.5 multiplied by the width, which is 10, then 2.4 times 10. Wait, if you need me to talk through that again. Perfect. This result would have been, say it please. So this is 164 there. Sorry, I need to write that in. What's the final result? Please show me your hands if you correctly found that to be 203. 2 points. Wait, you need me to talk more? You good? Yeah. So go to 5 now. So go to page 5. Go. Any questions on page 5?
I'm still confused. Like, does it matter on when you're writing an integral what number you have on the top and the bottom of the S?
Awesome question. So mathematically, you can actually do it either way. Like I can write the integral from 10 to 70 of the velocity will equal the change in the height of the rocket between those two times. Or I can switch and write like this. And the equation is still valid. But what is important is whatever's here has to be here. And here has to be here. So you can switch it. I do find that this tends to lead to mistakes. So I teach, let's always go from lesser to more, which means on a graph we'd always be going from left to right. But mathematically it's valid to do either. You can even do this. You can say, if I switch the limits, these two integrals actually are going to give opposite values in terms of the sign. Like we estimated this integral to be a value of 2020. If I switch the limits and perform the integral again, I'm going backwards. I'm going from 70 to 10, which means the change in time will always be negative. So this result would be negative 2020. Did that answer your question? 2 points. Any other questions? Oh, please.
Wait, that one just, if it's negative 2020, how is it the same as positive 2020?
So remember, this value is representing the fact that the rocket's, in this case, is going upward, and it starts at some height. I don't know if they told us, right? H of 10 is 95. So we're down here at time 10, and our height is 95. And then in the next 60 seconds, the height's going to change by an amount of 2020. So the space here between, my lines are a little quicker, this distance is 2020, which gives us this new height up here at time 70. And what's 95 plus the 20 is 2115, right? You with me? Well, if we do the integral backwards, this comes out to be negative 2020. But this is equal to the reverse of the two. So it's taking the lower height minus the upper height. So that's negative as well. That's why it's still true.
So they're both negative.
Yeah,
Okay.
you have to switch. So you notice this is h of 70 minus h of 10. Now I've got h of 10 minus h of 70. That's partly why, 2 points for Rachel, why I don't really like discussing this very much, because it just causes confusion. Like people pretty soon are doing it both ways, and then they're mixed up, and they're getting the signs all wrong. So I just always go left to right.
Okay.
Good question. Even though mathematically you can switch it. So. Anybody else? Okay, looking here just to pay some extra credit. Please raise your hand if you were able to finish page 5 successfully. 2 points. Go to 6. Go. raise your hand if you have these answers. Who has these? Who has these two here? More point? You want to talk about it?
Wouldn't maybe 2120?
This one here?
Yeah.
I'm not sure, to be honest. I don't remember. So what's the answer here? 2120. Raise your hand if you have 2120. Much better. Thank you. 2 points for Isaac. Go to page 7. Go.
Wait, question.
Oh, yeah, please.
How do you know if they're consistent on G?
Oh, gotcha. So the idea, the reason I wrote that was I was hoping you would notice that I was kind of talking to Hayden about, Drew about this, sorry. The fact that what we're doing is this is the actual velocity. So what I'd really like to do is I'd like to take a velocity of 5 and multiply that velocity by 1/10 of a second, like a very short amount of time. Then take the next velocity, 5.1, multiply by 1/10 of a second. Take the next velocity, 5.2, et cetera, et cetera. So that's my ideal situation, which means I would be finding the area of very narrow rectangles, and each narrow rectangular area would represent the change in position of the rocket for that very short time period. So that's the ideal that I would be wanting. When I make my approximation, it's as though I ignore all of that and just say, well, let's just pretend the velocity is 5 for an entire 20 seconds. So my plot ends up looking like this, just straight across for 20 seconds. Then for the next 20 seconds, I'm at a velocity of 22. And so this green area is representing the computations that I'm performing here.
Yeah.
And so when I add up all those green areas, I end up with the 2120 as my estimate for how much the rocket's position changed. Because that area is less than the ideal area, I know this is an underestimate.
And you can see that on the graph.
So that feel good?
Yeah.
And then when I go to, I'm probably going too slow, sorry. When I go to the right-hand Riemann sum, it's as though the area where the velocity is 22 for the first 20 seconds. So that's definitely an overestimate. And so these numbers are consistent with that in that this one is lower than that one. That's all.
Oh, okay.
Not a great answer on my part, but did that help a
Yeah,
little?
oh yeah.
2 points for Rachel. Anybody else? Keep going. Go to 7. Okay, let me talk for a minute. I forgot I hadn't shown you this. My apologies. Part A says, use the graph to illustrate what a trapezoidal Riemann sum looks like. So what I've drawn here is I started out doing the thin rectangles again. That's the ideal. Let's clear that off for a second. Okay, for trapezoidal, if I'm integrating from 0 to 70, velocity multiplied by change in time, I need to have those subintervals. So this is another example of don't read quickly. Student yesterday scored 76 on the first test, 97 on the retake. And really all she did differently was just slow down. Like she just got too rushed. So don't go fast. So 0 to 20, 20 to 30, and then 30 to 70. So you look at the first subinterval, you need to pick a velocity. That's what the integral is telling you. We've already talked about how if you're doing left, you pick the left velocity, middle velocity, right velocity. For trapezoidal, you still need a velocity. But the way you calculate that velocity is you pick both the left and the right, and you combine them into a single velocity. So just say it out loud. How do you take two velocities and create one? Average them. So I add the two. So you got 1/2. So take those two added together, and then dividing by 2 is the same as multiplying by 1/2. So this is the velocity I'm going to use for this first time interval. I multiply that by the change in time for the first time interval, giving me that. Any questions so far? Okay, the drawing is a bit unexpected. Here's why. I can never remember, but this is the actual formula for the area of a trapezoid. So that's where the name comes from. So the way they draw the representation is they say, well, the base of the trapezoid is 20. That's that dimension. The height on one side is 5. The height on the other side is 22.
Yeah,
Go ahead.
the equation is base 1 plus base 2 times 1. Isn't it?
There's a 1/2 in there because it's a trapezoid.
Yeah, it's base 1 plus base 2 divided by 2.
Oh, there you
times
go.
height, yeah.
Perfect. Yeah. No, you got it.
Yeah.
So we're good?
Yes.
Excellent. So I take this height. Good memory. I don't remember that one, Allison. So I take this height, which is 5, and then the other height, which is 22. And to create the trapezoid, I connect the two heights with a straight line. It's a little hard to see, but that straight line cuts just barely under the curve. So in this case, the trapezoidal Riemann sum is going to be an underestimate. Wait if you want me to say that again. So the 20 is this dimension, the height of 5 on the left, the height of 5 on the right, 22 on the right. To create the trapezoid, those two heights get connected by a straight line. Because this is a curve that's concave down, it's a little hard to see there, but if I exaggerate it, you're doing something like this. And then the straight line cuts under the curve. So ideally, we'd be wanting the area outlined by the curve, but instead we get the trapezoidal area. Hence, this trapezoidal Riemann sum will be an underestimate. Wait, if you want me to talk some more about that.
So you just determine like if the trapezoidal one's under or over depending on the concavity?
It is. Whether a trapezoidal Riemann sum is an under or overestimate is entirely dependent upon the concavity of the curve. It's perfect. 2 for Brennan. Anybody else? So go, keep working. Good work. Keep going. So what's the answer here? Please raise your hand if you have, did that correctly, Shona? 2 points, wave if you want me to talk about it. Cool. The last one is, what's the answer? Got it? 1660.
Yeah.
How many agree? 2 more. Question? Just keep going. Page 8.
You just give us a negative. That means all we do is just plug in negatives. Because we want to get a total distance out.
Oh, yeah, that doesn't make it if you're going
That's just not fun. That's okay for that. Sounds fun. Dad's
So what's the value here? The trapezoidal Riemann sum, what's the value?
Negative 75.
Say again?
Negative 75.
244.
So show me hands if you were able to get negative 75 here. Show me. 2 point. Then added to the 14 gives us negative 61, is that right? Yep. Okay, anyone want to talk about any part of this? Please.
I have a question. So we did 3 sum intervals between 20 and 40, correct? Okay. So I get that there's like 2 things, but I don't get why I'm
You got to talk some more about church.
okay, well, here's the thing. When I first did it, I did like between 20 and 25, the average between those, 25 and 30, and 32, I mean 25 and 32, and 32 and 40. But I didn't see it.
Yeah, you should have 3.
You should?
Because you have 3 subintervals. So you should have 1, 2, 3 different computations.
I was doing it right. Never mind, I figured it out.
Anybody else? Please, go ahead.
We go over right or left.
Yes.
Okay.
So silence for just a minute.
Just why is it so red?
Shh, just quiet for a moment. Okay, so the key is to remember that speed is the absolute value of velocity. So as I'm tracing this graph of velocity, what's strange is the following. If they will ask both questions, they'll say, when is the speed increasing? And they'll say, when is the velocity increasing? Answering the velocity question is straightforward. The velocity is increasing here. The velocity is also increasing here. Wave if you need me to do that again. So that's when the velocity is increasing. Better, good. Speed, however, is different. So along this path, the velocity is 3, then 4, then 5. So the speed is the same, 3, 4, 5. That means the speed is increasing along that path. Along this path, the velocity is 5, 4, 3, 2, 1. Speed is the same, so speed is decreasing. The velocity continues to decrease. The speed doesn't. Because here the speed is positive 2. Here the speed is positive 3. Speed is positive 4. So along this path right there, the speed is actually increasing. Did that answer your question? Yeah. 2 points. Similar here, speed is increasing again. So along here, the velocity is increasing, the speed is decreasing because the velocity goes -10, -8, -6, but the speed goes 10, 8, 6. You don't want me to repeat this way. Cool. Keep going.
Yeah.
We're a little short on time, so I'm going to talk now for the last 5 minutes. Okay, the particle is at rest when the velocity is 0. So wait if you need more explanation on that, but I'm thinking that's pretty straightforward. Okay? It says use the graph to estimate the time when the particle changes direction. During this time period, the velocity is always positive. That means the particle is moving to the right. So all eyes on the board for just a moment. Everybody look at the board. Please don't forget that tells you the following. This area here that I'm now highlighting, get the highlighter turned on. This area here coincides perfectly to how many meters the particle moves to the right. Question. Awesome. Then this area coincides perfectly with how many meters the particle moves to the left. Then the particle will move back to the right a small amount. Like that. Wave if you want me to repeat any of that.
Just goes straight down. Okay.
You okay with that?
Yeah.
So, changing direction is easy. When the velocity changes sign, the particle changes direction. So in this case, the times when the particle is at rest are exactly the same as the times when the particle changes direction. Please.
Could that be different?
Yes. So if I draw a graph of velocity that looks like this, v of t, then my graph of velocity has this appearance. There will be 2 times when the velocity is 0, meaning the particle is at rest, but the particle will never change direction. It's always moving to the right. It like moves to the right, stops for an instant, and then starts going again. 2 points. Who else? Okay, back here. It says at time equals 0, the particle is 3 meters from the origin. So here's the origin. Origin is always location 0. Origin, okay, this is the origin of the graph, but the origin here is different. So it's location 0. Here's the particle. It says, is the particle moving away or towards at time equal 8? Well, from time 0 until time 8, the velocity was always positive. So the particle was here and it moved to the right. So during all of this time, the particle is still moving away from the origin. The way you justify that is you tell the grader the particle's position at time 0 is positive. So the particle starts to the right. The velocity is then positive for the next 8 seconds. So the particle has to be moving away from the origin. Wave if you want me to repeat that.
That's how you justify your answer.
The way they want it justified is they want a comparison between the position and the velocity. I gave a slightly more difficult question than I've ever seen them ask. They usually ask something a little simpler. They just say, at a certain time, is the particle moving away or towards? And all you have to do is identify where is the particle at that moment and what is the velocity at that moment. And then you'll know whether the particle is moving away or towards the origin. So we'll practice that some more. So, 2 for Elijah, please.
Does it matter if we use words to explain?
No, words are fine. So we'll practice that some more. So, okay, these 2 go pretty fast, so I'm going to leave that alone for a second. We got 2 more minutes. Go to 10. And the homework's pretty simple tonight. Just finish the packet. It only goes to problem 11. The answers are in the back. So, okay, look here at the graph. Make sense of this, and it's easy to remember. This object, the other graph was a little easier to see, went to the right by this amount, then went to the left by a larger amount. So watch my hands. Here's the object at location 3. It goes to the right. Now it goes to the left more. So it ends up over here. Got it? And it goes to the right a little bit. So the change in position is negative. The difference between where the particle started and where the particle ends is a negative number. Question? Awesome. But the total distance traveled is going to be a positive number because you just add up the distance. You say I went to the right this much, plus this much more to the left, plus this much more to the right. So the equation for finding total distance is exactly the same as change in position, except you don't count anything as negative. So look at my Riemann sum. I'm going from 8 to 40. I'm doing a right Riemann sum, so I'm picking these values, but I count all of them as positive because of the absolute value sign. Good work. Perfect.
I just don't